Assalamu alaikum. Today I will show you the first project of the computer organization course. In the project files I have provided a link to our project. If you go to that link, you can directly run it on your browser by clicking this button in here. In here, as you can see, we have our project. You can also look for the project files that I have provided. So I have written some demos to run and show you that actually the project works. So if we run this code in here, let me go from the top. In the first part, we have we have added two numbers, which is t0 is 5 and t1 is 3. And if you sum them up in here, it is 8, as you can see. And we have done addition with changing orders. If we change the order, it doesn't change the result, as you know. So it's 8 again. So for the substitution, if you substitute t0 from t1 from t0, which is 5 minus 3, it is 2 in here. And if you do vice versa, you will get minus 2, which is in 2's complement form, as you know. So for the logic operators, we have initialized t0 and t1. t0 is 0 f 0 f, and t1 is f f 0 0. And you can see them in here as well. If we AND those two, we end up getting 0 f 0 0. And if we OR these two, we get 0, we get f f 0 f. And also if we XOR them, we get f 0 0 f. So if we AND I the t0, which is this one, if we AND I it with 0 0 0 f, with that we get 0 0 0 f. And if we OR I with 0 0 0 f, with t1, which is this one, we get we get f f 0 f if you OR I with that. So that's it for all logical operators, and we have shift operators in here. Actually not shift, sorry, the set less than operators. So in the first part we are comparing 5 and 3, since 5 is not less than 3, result is 0, and is 3 less than 5? Yes, and therefore the result is 1. And is 3 less than 4? Actually, sorry, is t0 is 5? Is that less than 4? No, that's why the result is 0. And is 3 less than 4? Yes, that results in 1. So for shift and load upper immediate, I have just loaded 8 7 6 5 4 3 2 1 T0 and loaded it. Yeah, I mean I stored it into data memory in here. So we have done it. So after that we have shifted it 1 byte, which is 4, actually not 1 byte, we have shifted it 4 bits left, and this is original, this is shifted value, and shifted to right, and arithmetic shift to the right. So for the multiplication and division, we have multiplied 5 with 3, which results in 15, and we have stored its low and high values in here. This is low value, this is high value, and also we have divided 5 to 3, which results 1, and the remainder is 2, as you can see in here. So that's all for these operators. I have made a demo to compute factorial of a number. So in this demo we are computing factorial of 8. If you run this, as you can see, the factorial. Let's check if this value is correct. So let's convert it to decimal. As you can see, it is 4320. If we check the factorial 8, it is 4320. So that shows that this demo works, the factorial computation works, and you can see how it works. You can check the code for more information how I implemented it. I'm not going to explain it deeply. And for the Fibonacci, for the last demo, I have provided a Fibonacci number calculator. If you run it, the values are stored in bytes. To test the load store byte, I have stored them in bytes, as you can see. 1, 1, 2, 3, 5, 8, and it goes on like that. 8 and 13 and 21 and 34, I guess. It goes on like that. It goes up to 13th Fibonacci number. Let's check that as well. As you can see, it is 233. If you check the 13th Fibonacci number, actually it is this one is not correct. The actual number is it is actually 233. Yeah, as you can see, the correct number is 233. So thank you for listening me as I as I provided, as I said, you can directly go to the provided link to run the application in your browser. Oh, by the way, let me explain one thing I forgot. I will just briefly go over how this program actually works. So this part will take a little bit longer to explain it. So let's start by the HTML, CSS, JavaScript. Where is the script? Yeah, it's in here. And we have tokens, we have a parser, we have a compiler, and we have a MIPS simulator. So if we go from the tokens, we have all values, the machine code representation of the instructions in here in a dictionary format. As you can see, we have all opcodes and function codes in here. Also, I have provided the register codes in here as well. So if you go to parser, the parser basically parses the instruction into parts by using regular expressions. By using the regular expressions I have provided in here, it parses it into parts. For example, if you parse an add function in R-type, it gets the opcode RD, opcode RD, RS, RT values in here. So, and that's how it is parsing it. So after parsing the instruction into parts, we have a compiler to compile the MIPS code into machine code. So it's basically goes to the tokens and looks up for the machine code equivalent value from the tokens and puts the value in here. And the one thing that I have added in here is convert immediate to binary. This function takes the immediate value. It doesn't matter what's this format is. Not it takes any format actually. You can input it negative decimal, decimal, or hexadecimal, or you can provide binary. It doesn't matter. It converts it into binary format in 2's complement. You also provide the length of the output. I have set it into sometimes 16 for load store, for example, and I have I-type instructions have 16 length of input immediate value, and sometimes I have set it into 24. It was, I guess, for actually 26 for J-type instructions. So this compiler basically gets the parsed instruction and turns it into a machine code. And this is how actually a compiler works. It gets the code and it converts it into machine code. So in the MIPS simulator, we have registers for with 32 elements in it, and we have instruction memory and data memory with 1 KB of storage each. And we have a program counter, high, low, and we have a current instruction, and the current instruction in assembly code, and we have opcode, rs, rt, rd, shift amount, function code, immediate target values of the current instruction we are working. So the set instruction memory takes in the assembly code and the binary machine code. Actually, we also store the binary machine code and the assembly code, both of those, in our instruction memory. So we have a setter method in here to set those. Also, we have a instruction memory length, which sets the provided input length to run that many cycles. In the instruction does not need to be 1 KB in every run. So if it's less than 1 KB, it stops at that length. So for the fetching, we have a fetch instruction in here. It gets from the it basically fetches the next instruction and updates the program counter by increasing it by 4. And we have a step in here. In a step, we have a fetch, and we have and if the instruction is not undefined, actually, we parse the instruction in by its machine code into parts, and we then execute it. So we have run function in here, and we have a run until end. The run until end basically runs every instruction until the end. So the parse machine code, what it does, it gets the instruction and it parses it into opcode, rs, rt, rd, shift amount, function code, immediate, and target. As I mentioned, these are for storing the current instruction into parts. So after that, we have an execute function in here. It gets it's a basic switch case, and it switches and cases through the opcode and function code to call the functions of each instruction. So after that, we have the implementation of those functions in here: add, subtract, and, or, XOR, set less than, GR, shift left logical, shift right logical, shift right arithmetic, move from high, move from low, and multiply, divide, branch equal, branch not equal, add I, set less than I. So we have all those implementations in here. I will go through the most trickiest ones. So for example, for multiplication, this was a tricky one. So you just multiply rs and rt, and you convert the I converted the result into 64-bit number, and then I have sliced it into 32 bits, and the lower part is stored in low and higher part is stored in high. So for the division, we have dividend and divisor, rs and rt, and if it's the divisor is 0, then it throws an error, division by 0 error. And we have quotient and remainder in here, as you know, and we store the quotient in low and remainder in high. we have branch equal, branch not equal, and that I set less than I, and I. These are easy, and I am skipping those. So for the load byte, this was a bit tricky. So I will explain load byte and store byte. Those are a bit tricky. So the rest are easy. So the load byte is basically we getting the byte address in here, and after that we are computing the word address by um, after we compute the word address, we get that word, and we are setting the start and end of the end index of the word, which the target byte is in. So after that we slice the word, and after that we set the signed extended value of the RT. So in this load byte, one thing is important. I have used two binary string function in here, which I implemented in the below. So I have used binary string because we needed to signed extended the output of 2 bytes, so that's why I did that. It's easier to signed extend in binary format, as you know. So for the store byte, we have computed byte address, we have computed word address, we have fetched the word, and we have computed start and end, and after that we write the word as is from 0 to start, and we put our input into between of those start and end, and we compute the rest. We put back the rest of the word. I mean, we are, for example, slicing a byte from a word and putting our byte instead of that sliced part, and we are combining the words together to put our byte into those spots. So that's how I did it, and after that we store it into the data memory. So I will just briefly go through the functions that I have implemented. I will not go deep into the implementation of that. The parse int32 takes an unsigned, actually sorry, the parse int32 is the same as parseInt function, the default parseInt function in JavaScript. The parseInt function takes any value. You just need to provide the radix of it, if it's base 10 or if it's base 8, or if it's a binary number or hexadecimal number or decimal number. You need to provide it in the radix, and you provide the input string as well. The default parseInt function parses the value into a number, but it is not in 2's complement format. It just puts a negative sign at the beginning of the number if it's negative. So I've made it so that it is in 2's complement form. So so for the parseInt, that's it. So for the signed int, it takes in an unsigned integer number, and it gives outputs the signed integer value of that. It's in 32 bits. So for the sign extent, it signs extends a value by in binary format actually. So for the to hex string, it takes any number and actually sorry, it takes a decimal number and it converts it into a hex string which is in 2's complement form. And the two binary string function converts a decimal number into a binary string in 2's complement again. The 2's complement takes a binary string and makes it 2's complement. And yeah, actually, the 2's complement function takes the 2's complement of the provided binary number in string format. Yeah. So I will not go deep in the scripting and CSS and the HTML styling and HTML. I'm not going to deep into those because that's the front end of the project, which is not related to computer organization actually. So that's all. Thank you for listening me.